Next speaker will be Björn Lindman from NTU, and he will talk about association between amphiphilic polyelectrolytes and surfactants.
So, good morning again. And first of all, I would like to thank Lars and his staff for all the work on this meeting, and the Institute of Advanced Studies for arranging everything. And then, of course, I would like to thank the organizers for letting me give this talk. It was actually supposed to be a reserved talk put at the end, but then there was a cancellation, so Lars put it here. So I would like to talk now about a much simpler problem than we have heard about, and this is about polyelectrolyte surfactant interactions, where we have been active for quite some time. And in particular, we have noted that the amphiphilicity of the polymer is very important. So first of all, you can see here three addresses, and we are now here in Singapore with very nice and mild winters. So our life goes between these three places. This is the triangle that determines our life nowadays, and of course this will be very much season dependent where we are. So for our Asian colleagues, just to indicate that Sweden and Portugal, they are countries, small countries in the outskirts of Europe, so in the extreme sides. Okay, so in Portugal, we belong to Coimbra University, very old university from the 1200s, and they have a special privilege that the old royal palace belongs to the university. It was the capital of Portugal before Lisbon, so very nice. In Lund, we are not so fancy, but we also have a quite old university from the 1600s. So there are many people who have contributed to the results. I will present some scattered results on this topic. So there are people in Lund, Coimbra, Singapore. So in Lund, I mean my colleagues Lennart Picolell and Tommy Nylander. In Coimbra, Maria, Miguel, and Philip Antunes, and so on. And in Singapore, we were introduced to NTU by Lars and his group in biological sciences. Now we are located in material science and engineering, and also we collaborate there with Procter & Gamble, and different companies have supported this. And this is the problem that we started to address long ago, that if you mix surfactant and oppositely charged polymer, you will get a phase separation very closely to polyelectrolyte complexes that you hear about. However, in most formulations, you don't want to have phase separation. So how can we control this? And and in particular, in some applications, you want to deposit a polymer onto a surface. So how can we control this? How can we learn about this? And we can have different ideas. There must be some attraction between polymer and surface and so on. But this proved not to be the case. So you have to go to other aspects. So one problem that we started to work on long ago were polyelectrolyte deposition in this 2-in-1 shampoo. So you have a shampoo with an anionic surfactant and a cationic polymer. There are also other additives, but they are less important for the action. So we want to deposit the cationic polymer for conditioning, but we then have anionic surfactant plus something else for cleansing. We have, of course, surfactant in large excess. So, and the problem is then that the cationic polymer, if we put it alone on hair, it will adsorb, but not in the presence of surfactant. So, and this is a phase diagram point. So we started long ago to work on, we had a tradition of surfactant work in Lund, but then companies told us that the most important is to look on the interactions with polymers. So we started two PhD theses very long ago, one with Oxnobel and one with a pharmaceutical company in Uppsala, now GE Healthcare. And one student, and he started with, it was with hyaluronic acid and cationic surfactant because they were interested in eye surgery. So, and this student, he realized very soon that you have to have a three-dimensional representation of the phase diagram to understand what's going on. And this was a good starting point for consideration. So normally you work in this mixing plane. So you mix the polyelectrolyte, the surfactant and water, and then you see that you have phase separation. But phase separation doesn't necessarily take case in this plane. And then, of course, later it was found out that what comes out of solution is not a simple precipitate or gel, but it's very much structured. In Lund, Asat Bilalov and Ulf Olsson worked on this, but of course there were very important prior work of Joachim Redler and Cyrus Safinja. So you get lamellar phases, you get hexagonal phases and cubic phases, depending on the and also it's of course easy to realize that if you add electrolyte to such system, then the attraction gets weaker, and you can eliminate phase separation to get miscibility. And if you add a lot of electrolyte, you actually get a segregative phase separation. So the micelles go to one phase and the polymer to another, which is the typical case, of course, when you have non-ionic systems, when you have no electrostatics, then they will segregate in this way. Okay, this is a little basic. So now the phase diagram, the approach to this, how we solve this problem. So we are mixing surfactant, oppositely charged polyelectrolyte. But the reason why we need 3 dimensions is that we have another electrolyte, which is the polyion with the surfactant ion as counterion. And we have the counterions combined together. Then we have water. So we have actually 5 components in such a system. And it appears that what plays very important role is the simple salt to understand what's going on. So this is the conventional representation of the phase diagram. But it's much better to look on this representation where we have the complex salt, because it's the complex salt that we want to put on the hair. And then we have the simple salt. And we know that if we take, so of course, I mean, there is a self-screening effect. I should have said this, that if you have a closed two-phase region here, so at higher polyelectrolyte surfactant concentration, you have miscibilities, you have a homogeneous phase because of a self-screening effect. And so you are here in the phase diagram. And then if you dilute such a system, then you move, of course, towards the water corner. And so from the homogeneous formulation in the shampoo, you move into the two-phase region, and you get deposition of the complex salt. And the more water you add, the more concentrated will the system be. So what is happening here? What's happening when we add water is that we dilute the simple salt, because the simple salt is, of course, there, even if you didn't add any salt, because it comes from the counterions. So dilution of the simple salt, that's what causes phase separation. So now we can wonder if in the shampoo it's so simple that it's just the solvency effect. When we have our shampoo, it doesn't, the polyelectrolyte doesn't absorb on hair because it's bound to the surfactant. You have excess of surfactant. So there is no absorption before you add water to the system. then you start to have deposition. And then if you add more water, then the polymer will stay, but the surfactant will move away, hopefully taking the soil with it. And this has to be described in this three-dimensional phase diagram. So then we wanted to check if this simple solvency effect really is what works. And because we can manipulate then the phase diagram and see what happens then with the deposition. And then, so we were interested in, the industry was interested in roles of molecular weight, charge density, polarity, hydrophobic groups, and also kinetic aspects of this. So Tommy Nylander, my colleague in Lund, he's an expert on ellipsometry. So we started some work on ellipsometry, and what you see in ellipsometry, you pre-absorb the polymer on the surface, then you add, this is on a polar surface, you add surfactant, anionic surfactant. Nothing happens until you reach the so-called critical association concentration, where the surfactant starts to bind to the polymer, and then you get adsorption, and you get much more on the surface. When you add more surfactant, everything goes away from the surface. So at higher surfactant concentration, nothing is adsorbed. So it's removed when you have a lot of surfactant. Now it was interesting to start out here with the normal conditions in the shampoo to dilute and see what happens. And actually, here we have a condition with 10 millimolar SDS and a low amount of polymer. Nothing adsorbs. At 1,000 seconds, we start to rinse, so we add huge amounts of water. This is in situ process. And then we see that we get enormous deposition on the surface. So adding water deposits the polymer surfactant complex. And this is the reason. This was the first experiments was Eiji Terada from Kao company in Japan and student Julia Samoshina. So there we see a jump on rinsing. And then we studied different effects on this, to verify this solvency model. For example, we added a little salt to the water. If we had salt, as you saw, we decreased the two-phase region. So we should have less deposition. And indeed, if we have 10 millimolar sodium chloride, you get much less deposition than if you have distilled water. So much less deposition with salt. Another question that also was important in developing such system was, should we have hydrophobic groups on the polymer or not? We could think of it with hydrophobic groups, the polymer would adsorb better to hair. But actually, with hydrophobic groups, you get almost no deposition. Why is that? The reason is that the two-phase region is much smaller. So you eliminate, and that high enough hydrophobic content of the polymer, you eliminate the two-phase region completely. So therefore, you can never have any deposition. So you never get the hydrophobically modified polymer onto the hair. So almost no deposition with hydrophobically modified. So this is again described by the phase diagram. So what we need to have then is, can they describe now? First of all, we cannot have precipitation in the shampoo. We don't want two phases. This means that you have to have excess surfactant binding. So if we bind SDS to a cationic polymer, then we see two binding steps. One to charge neutrality, and then the second one and this is due to some hydrophobic character of the polymer. So you need to have charge reversal in the system. And in a simple experiment, you can illustrate this. This is when you had the polymer in solution, add surfactant, you have a clear solution. When it starts to bind, you get a turbid solution, phase separation. But then if you add more surfactant, you get a clear solution again. So you get redissolution. And this is essentially for such systems. So when do we get pre-dissolution? If we have a very polar polymer, it doesn't work because we only bind to charge neutralization. We don't bind excess surfactant. So we need some hydrophobic character. Then we get redissolution. But we cannot have strong hydrophobic groups because then we get a very small phase separation region, so we can never get deposition. So the balance is very important there. So this is a summary slide that Jens Norman, who worked on a postdoc project with BASF on this issue, he found that there is a certain path that you need to follow. So if we have here, we have the polyelectrolyte and the surfactant molecule. And the surfactant molecule bind. And you need to have, first of all, you have to have binding up to charge neutrality. But if it stops there, if it stops at charge neutrality and doesn't bind more, it doesn't work. You need to have an excess surfactant binding. But then if you add water, the surfactant must leave the complex. If it's too strongly bound, it doesn't leave, and then you cannot get any redeposition. This is what happens with hydrophobically modified polymers. Okay, so the binding isotherm is important, and it depends on hydrophobicity of the polyion. And it works with deposition, and we can see it in situ. And you should start, the formulation should be close to the two-phase region. And we see that deposition is always related to solvency, but not to polymer surfactant interaction. And then we also have to take into account the irreversibility effects, but I don't mention this here. So then about surface polarity. Again, since it's a solvency effect, this doesn't actually play any major role. It's only the phase diagram. So if we have more hydrophobic healthy hair or more ionized damaged hair, it doesn't matter so much for the deposition. So here is how we can summarize it. You get deposition when you get surfactant adsorption, and you have phase separation. Then you get desorption when you add more surfactant, and when you rinse, you get deposition. So then another amphiphilic polymer. Actually, it appeared to be very similar problem as the hair shampoo to bind surfactant to DNA. This is, of course, a highly charged amphiphilic polymer, and so it should bind a lot of surfactant. And this is work now by Rita Diaz, starting when she was a student and continuing. And she started with looking on this familiar compaction of DNA. You compact DNA by oppositely charged surfactant. This has been worked before by Yoshikawa in Japan on polymers and other systems. We started on surfactants, and you see this compaction because you neutralize the charge. So Rita also made then phase diagrams, and I will be brief here. This is early work, and the chain length of the surfactant is exactly in the right trend, that the longer chain surfactant, which has more highly charged micelles, will phase separate DNA more than short chain surfactant. In her PhD work, Rita could not see any redissolution. She worked hard on this, but there was no redissolution, which would be, we were quite sure that the DNA, since it's hydrophobic, should lead to, but later she came back then this and could show that this was actually a kinetic effect, and I will have a slide later. So she didn't see redissolution at first. And also, but what she saw was that the hydrophobicity plays a role. So when she compared single-stranded DNA and double-stranded DNA, she saw stronger association for for single-stranded, where the hydrophobic groups are more exposed. So you have a lower surfactant concentration. So these are the precipitation lines. Adding surfactant, you get precipitation here. And you have much lower concentration for single-stranded DNA. So this is what happened when she came back to these problems some year ago about redissolution. Then she actually, by having another mixing protocol, she could clearly see that there is, in the phase map, is a miscibility gap. So at low surfactant, at high surfactant, you have actually homogeneous solution. And she confirmed this by electrophoretic measurements. She could see both negative mobility at low surfactant concentrations and positive mobility of the DNA surfactant complexes at high surfactant concentrations. We can also look on this on surfaces, and this is work with Tom Nylander and Cecilia Leal in Lund. DNA alone adsorbs on a hydrophobic surface because it has some hydrophobic character. It adsorbs in a very expanded way. So this is the thickness. It's very expanded because of the osmotic swelling, of course. When we add surfactant, when we add the cationic surfactant here, we see dramatic changes. You get an enormous increase in the adsorption, but a very compact layer. The layer goes now to just a couple of nanometers from 20 or so. So you see a compaction also on the surface of DNA. When we rinse, so this is again ellipsometry, in situ ellipsometry, on rinsing, surfactant goes away and you get a reswelling on the surface. So DNA reswells then. These were some examples. Then some years ago, we had collaboration with Lars and his group on histone complex nucleosome core particles. I will only mention this very briefly, but it fits very well into the general picture. There are presentations of Lars' co-workers during the meeting. So we worked on nucleosome core particles and on these arrays core particles, and adding cationic liposomes, for example, and mixed charged liposomes. And one very interesting observation was that here are some X-ray studies, and they could see then that you form lamellar ordered structures, and when you add high amounts of liposomes. So a general result was that the histones are expelled from the NCPs or from the arrays. So the DNA lipid complex is stronger when you have higher charge densities in the liposome, but not otherwise. So do I still have a few minutes? Or? Still have a few minutes. Okay. Then I turn to a very different problem. And this is, these are some polymers which are used in cosmetic formulations, but have some striking properties. This is work due to Philip Antunes and Luis Alves in Lund, together with BASF in Düsseldorf. And it's work on polyelectrolytes, which are both strongly hydrophobic and cross-linked. So microgel particles. And to these are added surfactant molecules. So we have a double network in a way. We have a hydrophobic and network and also a covalent network. And then one interesting thing is they are then used together with surfactants. And one very striking observation is, so these are polyacrylate based. So at low pH, they have no charge. When we add SDS to them, we see 7 orders of magnitude increase in viscosity. Because, of course, what happens is that SDS binds to these microreal particles, and then you get an enormous swelling. In the same way, it happens the same with pH. If you have them at low pH, you have a very low viscosity, but then you have 7 orders of magnitude increase in viscosity when you increase pH and you ionize the carboxylic acid groups. So ionization and binding of ionic surfactant works in the same way. So they also become clear at higher pH or at higher surfactant, because then you expand the microreal particles very much, so there is no contrast between the particles. So what happens at low pH, they are very compact, but at high pH, they swell, or when you have bound a lot of anionic surfactant, they swell a lot. So then you have no contrast, so you see no scattering. So we can manipulate these microreal particles both with surfactant and with pH, can control the viscosity. So these were a few examples of the role of amphiphilic properties of polyelectrolytes in applications. And now in Singapore, we are involved in a project with Procter & Gamble, and our student, Rui, he's sitting somewhere here. Rui is sitting there. He will have a poster, so I recommend that you look on this. This is also related to hair conditioner. And with this, I would like to thank you very much for your attention.
Going back to the shampoo problem, it's a very complex system, of course.
Yes.
Of course, people take showers. People take showers in at different temperatures. Mm-hmm. What is the effect of temperature, and how do you formulate so it's not so sensitive to temperature changes?
Now, these polymers which are used are actually not so sensitive to temperature, and this phase separation due to opposite charges, it's only weakly dependent on temperature. So temperature actually doesn't play so role.
Even the solvency is not that dependent?
No, it's not so dependent. I mean, the problem you can have is with the Kraft point of the surfactant, but otherwise this interaction is not. If we use non-ionic polymers, but this is for other purposes, then you have a huge temperature sensitivity, but actually not for this process.
Thank you.
Other questions?
Hi, thank you for the really nice talk. Again, on the example of the shampoos, what happens if we are using harder water, for instance, with more calcium?
Yes, this is a disaster for this. And I think I had a slide there showing the salt effect. And so here. So even small amounts of salt. And the calcium is, of course, much worse. So calcium has two effects on this. First of all, the two-phase region gets much smaller. So it's much less chance for deposition. But also calcium will affect the Kraft point of the surfactant. So I cannot recommend this to have hard water.
And would there be a practical solution for that?
Yes, not to use hard water, but I mean surfactants. On the surfactant side, there are anionic surfactants which are not sensitive to hard water. They have been developed by industry. But this phase diagram, I don't think you can do much about as far, but we didn't work too much about this.
One more question.
Yeah, that a little bit on the nucleosomes. So I was wondering the situation where the nucleosomes are expelled. Does it have relevance to in vivo biology? I mean, is there situations when that might be happening?
Yes, that's a good question. I think I give it to Lars because actually we have not been much into the problem. But when you use cationic lipids in different formulations, of course, it's important with with the competition with histones. But Lars, you know this much better.
Normally you don't have cationic, you have sucralonic or negatively charged lipids in the nuclear lamina, which might be close to the chromatin in the nucleus. So maybe the situation is not as bad in that regard.
One hopes.
So with that, let's thank Professor Lindman.